A rocket weighing over 16,000 tons, traveling under an average thrust of 1.5 gravities, is aimed at the planet Mars while in opposition with Earth. The ship releases propulsion devices every 10 seconds. At the midpoint between planets, the ship turns 180 degrees and begins to decelerate, completing a brachistochrone trajectory, bringing the vehicle to a complete stop over Mars in preparation to land on its surface. This represents a massive expenditure of energy. To bring 16,000 tons of spaceship up to 1,100 kilometers per second, the propulsion system will harness 10.3 zettajoules of energy, 10.3 joules times 10 to the 21st power. This is equivalent to 2.5 billion megawatt hours, nearly a fifth of the United States' annual energy production from all sources. It accomplishes this by expending nearly 14,000 nuclear devices. A Hohmann transfer to Mars takes about 250 days. Rockets designed for rapid missions to Mars, such as SpaceX's Starship, use a large amount of fuel to shorten this period to around 90 to 150 days. A trip to Mars from Earth's surface will take 40 hours and 45 minutes using nuclear pulses. Riding to Mars on this vehicle takes less time than a flight around the world using commercial airliners. On this episode, we're going to gain an understanding of what constructing and operating these vehicles will demand from us. The indigenous United States Nuclear Pulse Program commissioned 6 ships at the end of 2034. When construction on the Freeman started, its original hull was intended to bear the name Sedalion. This planned 25,000-ton freight ship was eventually scaled back from its original proposal, and the partially completed pusher assembly would become the basis of the NPS-4, the Freeman, a multi-role exploration and manufacturing platform. Freeman was ultimately the 4th nuclear pulse ship to be laid to space, though construction on its system started before the NPS program had yet produced a completed vessel. While Freeman could not claim to be the first nuclear pulse vessel built in orbit, it was regarded as the first widely successful design and could be assembled entirely in orbit. All 3 vehicles manufactured prior to Freeman had necessitated frequent refits to expand their capabilities. The designers intended to resolve these learned problems and offer a standard design for future United States NPP vessels. The NPS Freeman is the 2nd Sedalion-class vessel commissioned under the Joint United States Space Force and Space Transit Authority Command. This spacecraft was mostly built from structural steel and aluminum components lofted to Earth orbit on first-generation uncrewed NPP vehicles, as well as on chemical rocket launches. Internal areas are accessible through small passages providing access to normally unused areas of the ship. Passages can be selectively pressurized when a short-sleeve environment is needed and are designed to accommodate man-portable equipment. Running part of the length of the central axis are a set of elevators, separate 3x3 meter cargo lifts, each with a pressurized load volume of 20 cubic meters for moving heavy equipment throughout the ship, and 4 smaller lifts for individual crew use. The elevators offer access to the crew areas, cargo, nuclear power plant, and device magazines. Multiple docking areas provide a rapid cargo ingress and egress capability, with a 8-meter wide forward docking node opening into the elevator column. 4 smaller docking ports above the magazine section allow for quick loading of pulse devices without using pressurized areas. A ring of work bays, each with an internal volume of 125 cubic meters, feature airlock capability, allowing several large objects to be assembled and berthed simultaneously. External manipulator arms can be deployed to assist in loading from this area, and dedicated airlocks allow for EVA. Station keeping, docking, and other low-energy maneuvers rely on the Freeman's orbital maneuver system, based on the reaction control system used widely in NASA's legacy space vehicles. The aerosine tetroxide hypergolic mixture is fed into a number of AJ-10166N maneuvering engines. The pusher plate's construction has several considerations. It is made of 15 centimeters of transuranic material and produces a localized magnetic pinch through its heavy element shield. This removable shield of radioactive material is non-ferromagnetic, so it has little insulating effect on the produced fields. A number of pumps and reservoirs along the pusher plate's rim replenishes a protective graphite-impregnated oil. Behind the plate is a series of powerful toroidal electromagnets, producing a magnetic pinch effect compressing fuel plasma before it can reach the pusher, which increases engine efficiency. A steel disc above the first stage absorber blocks magnetic fields, preventing interference with the magazine area. The magnetic field can also be disabled to accommodate long-range communications during acceleration periods with no detriment to operation. Inertia transfer is accomplished in two stages: a rapid compression volume with a wide weight distribution to absorb the initial impulse, followed by a stage of 8 pistons which provide controlled resistance to level out unexpected oscillations in the plate. The pistons can be manipulated using hydraulic pressure or electricity, connected to 8 independent linear actuators. These are not your typical linear electric motors. They employ superconductors maintained by liquid helium coolant. Disabling or emergency failure of the coolant loop will reduce power conversion efficiency, however, operation of the engine will not be adversely affected. Even the uncooled mechanisms provide the vehicle with a constant source of high-voltage power during operation. Electrical power produced by the piston alternator system, which is not used, can be stored in alkaline fuel cells at an acceptable efficiency. Regular operation of these cells consumes hydrogen and oxygen while producing water suitable for use by the crew. NPS Freeman has 2 solid-state fission reactors, each weighing about 400 tons, with a volume of 260 cubic meters. The self-contained reactors consume inert gas and hydrogen as they produce a peak combined output of 450 megawatts. The reactors are easily serviced or removed from the vehicle, having a closed coolant loop and dedicated electrical equipment. These reactors must be externally accessible so that their fuel material can be replaced and for other routine maintenance. This is in contrast to reactors which would be built into the structure of the vehicle with interfaces to monitor and replenish the fuel in a manner more akin to commercial mobile reactors on Earth. Minimal crew interaction with the power plants is a benefit of a closed-loop reactor and is an essential aspect of the Freeman's safe and consistent operation. These reactors are strongly redundant. Planned missions will frequently call for removal of one of these reactors to support construction operations. Pulse devices are ejected at a rate of once per second or slower, propelled by a reciprocating light gas piston. Failure of the hydrogen loop powering this piston will cause an electromagnetic launcher backup system to take over, and a tertiary mechanical redundancy can also be employed in the event of electrical failure. Should the vehicle lose both main and backup power, stores of pressurized inert gas can be used to launch the pulse devices. Payload mounting points around the Freeman's midsection are fitted with construction material, transport shuttles, additional device magazines, crew modules, or any other equipment demanded. The midsection has internal storage volume accessible by the crew, and these are loaded from the 8 work bays located just above. Freeman can ingress and egress cargo simultaneously, and the central elevator shafts can be used as temporary holding areas for cargo and equipment. A set of pressure vessels and slosh tanks store several materials demanded by the vehicle: water, liquid hydrogen, liquid oxygen, and replacement electrolyte for the fuel cell system. Other pressurized material includes aerosine and dinitrogen tetroxide, hypergolics used by the RCS system, and inert gas for equalizing pressure tanks and feeding the nuclear reactors. Crew compartments are arranged in 5 areas, pressurized volumes between 620 and 900 cubic meters. This totals about 4,000 cubic meters of crew space, or more than 4 times the internal pressurized volume of the International Space Station. Each compartment contains its own life support and storm cellar. 4 of these redundant sections are provisioned for habitation, with the 5th smaller area dedicated to vehicle control and mission work. 1 habitat section has access to external manipulator stations, allowing for remote experimentation and light manufacturing. The crew modules are oriented to provide artificial gravity during transit. The pusher plate's inertial distribution system smooths out acceleration pulses, allowing the crew to enjoy nearly constant perceived gravity. This would fluctuate between 0.8 and 1.4 gravities during high-power maneuvers. Safety protocols would be employed to minimize activity during acceleration, since the fluctuating gravity could cause accidents. The compartments are designed with the considerations for multiple gravity orientations. In an emergency, the Freeman can use axial or end-over-end rotation to provide felt gravity for the crew. It is worth mentioning that the high mass of NPS Freeman makes spin gravity unattractive in comparison to acceleration gravity imparted by the drive. NPP vessels tout the ability to burn their engine for the entirety of their maneuver, with minimal or no coasting, so relying on propulsion for gravity is a reasonable trade-off in this design. The Freeman carries both a provisional and constituent crew. The constituent crew will serve on the Freeman in a specialized role for about 6 years. These personnel are responsible for operation and mission control, consisting of primarily non-commissioned United States Space Force officers. The USSF has a multinational officer corps built into its nuclear pulse program, which hosts skill and ambition from several nations. The constituent crew can accomplish most mission tasks alone, but they are supported by the technical, scientific, and engineering experts who represent the provisional crew. Provisional crew members rotate on and off the Freeman as the mission requires, fulfilling needs for specific problems. Both the provisional and constituent crews are fully trained in operating the Freeman, meaning the wide responsibilities of long missions can be distributed. NPS Freeman allots for a passenger complement as well. This is roughly the same size as the crew and primarily consists of researchers and support staff. If needed, the payload section can be outfitted with additional crew modules to increase the passenger capacity of all Sedalion-class vessels. 6 configurable sections located on the exterior of the device magazine are positioned to make use of radiation produced by the pulse drive. The capability of these modules is dictated by the mission, typically deploying scientific instruments and communication equipment. Equipment modules with the utility roles can be expected to occupy a few of these sections at all times, providing pulsed energy. NPS Freeman can be expected to field 2 power production arrays at all times, one for conditioning ultrafast neutrinos, and another for converting proton flux into high-voltage current. The utility array is also where the Freeman's optical observatory is found, which can serve as a backup to the ship's primary navigational sensors. This observatory utilizes a 94-inch reflector and visible infrared sensor, leftover equipment from United States military programs now several decades old but still effective. This reflector is by no accident virtually identical to the mirror used on the Hubble, a design originally intended for spy satellites but now used on NPP ships to probe the atmospheres of Venus, Jupiter, and Saturn. When taking on cargo, Freeman can deploy a counterweighted cargo loading tether from a dedicated utility array. Typically, this loading tether is removed before departure from a loading location, freeing up space for additional scientific payload. The Freeman's thermal radiators are configured based on mission context. The craft can accomplish life support functions and low-intensity activity using secondary expandable radiators, but activation of the vehicle's nuclear power plants necessitates use of the larger folding radiator wings. Thermal radiators come in several sizes and are fitted to the Freeman while in dock. Considerations of safety and logistics will inform our discussion of mission parameters in the context of a series of typical maneuvers. These will see the Freeman arriving at the Terra Luna sphere of influence from a transfer orbit, having originated from Mars. The trajectory will take Freeman from deep space into a lunar capture, followed by a rendezvous with waiting cargo loading elements. We'll assume a partial crew rotation, with the incoming crew waiting in lunar orbit in a layover station. The waiting crew, lunar facilities, and the Freeman will all need to be protected in this scenario. NPS Freeman falls into the Earth's sphere of influence under thrust, decelerating as she shifts her flight path to pass within 20,000 kilometers of the Moon's surface. She is on the final burn of a Brachistochrone trajectory from a Mars in near conjunction. At the edge of Luna's gravitational influence, about 65,000 kilometers from the body, the Freeman has decelerated from an interplanetary top speed of 650 kilometers per second to just over 3 kilometers per second. The vessel will need to lose an additional 2 kilometers per second to acquire lunar orbit, a maneuver accomplished at periapsis with the use of 5 low-yield devices. Each device yields about 400 meters per second of delta V, and the moon capture maneuver takes less than a minute to complete. This maneuver exposes the moon's surface and orbital assets to radiation, and we can assume objects in lunar orbit will be at altitudes of between 100 and 1,000 kilometers, so it can be reasoned that both locations will be exposed to similar levels of radiation. Recall that Earth's atmosphere absorbs and scatters radiation, with large volumes of gas and vapor decreasing the range and energy of particles. In space, the radiation can travel much farther and retains its energy for longer. Ionizing radiation such as X-rays, alpha particles, and gamma rays are all problematic in space. However, we face a challenge modeling this situation using realistic numbers. To honestly do this, we'd need to figure out how much ionizing radiation our 5 to 20 kiloton devices produce, and then calculate their scattering behavior at a range of around 20,000 kilometers. Modeling the power output of electromagnetic radiation in three-dimensional space is not too difficult, but representing this behavior in particle streams produced by nuclear devices is well beyond the scope of this series. We'll simplify this problem to serve our discussion. Instead of calculating the device's power output, we'll extrapolate known thermal radiation from 20 kiloton testing devices and compare this to another data set. It is a reasonable way to encompass the known effects of ionizing radiation without having to calculate them. Thermonuclear devices tested for weapons use would have produced around 12 calories per square centimeter at a distance of 1.5 kilometers. This is about 6 times more intense than the light energy of the sun, and with no atmosphere to protect against ionizing radiation. This is a good way of thinking about the radiation produced by these devices, since measuring it will be more meaningful as a direct comparison to normal solar radiation. Solar radiation is planned for in vehicle and mission design, and is one of the most cited dangers of manned space exploration. A single 20 kiloton detonation at 1.5 kilometers emits 2 calories per square centimeter. The Sun, at 150 million kilometers, emits 12 calories per square centimeter per minute. A 20 kiloton detonation at 20,000 kilometers is magnitudes less intense than the effects of solar radiation at the distance of Earth and the Moon. At this range, thermal radiation is a non-issue due to dispersion. Even at close ranges of 10 to 50 kilometers, thermal radiation effects can be minimized by material design. Thermal radiation energy affects only a superficial layer of exposed material at lower intensities. Unsurprisingly, we can reason that thermal radiation is not a risk. We could have assumed this, but it's worth proving. Just like the Sun produces ionizing radiation, nuclear pulse devices do as well. The problem we have is to ascertain when the ionizing radiation produced by the pulse devices exceeds solar radiation, and we have a solution to this. By comparing the intensity of both sources' thermal radiations, as we just did, we know the magnitude of ionizing radiation relative between these two sources. The effect of solar radiation on objects in space can be directly compared with the effects a pulse device has on the Moon. The Sun produces much more radiation relative to a pulse device in this comparison, illustrating how a standard system of precautions, as are employed against solar radiation, can be used to establish safety guidelines for NPP vehicles. We can reasonably conclude from these estimates that a decelerating NPP vehicle will not pose an abnormal risk to lunar surface operations, since such installations already deal with the bigger issue of solar radiation on a daily basis. The Freeman's capture maneuver is preempted by a warning to all ground and orbital installations on the facing hemisphere of the Moon. This will restrict EVA activity and might confine workers in poorly shielded areas to storm cellars, just as a solar storm event might. A radiation condition alert might occur once, twice, or 5 times a month on Luna depending on solar activity and local traffic. These alert periods, lasting anywhere from 5 minutes to hours, are generally planned well in advance, but the lunar facilities conduct weekly emergency radiation drills as well to increase readiness. Risk management is the best way of thinking about radiation in space. Regardless of the locale, we can compare all of our risk sources to the constant flux of ionizing radiation emitted by the sun to have a realistic idea of how to rank threats. While illustrative, the comparison here is not direct and inherits uncertainties of device design and radiation composition. We cannot accurately determine the radiation effects on space environment because collecting data to inform on these effects will only be attainable as a result of operating these vehicles. My conclusion here is the same as the original designers of Orion's missions. The most practical way to establish safety protocols for Orion will be to conduct safe flight tests of these systems. The discussion of flight testing brings up an assertion made in planned orbital testing, which would have taken place between 1965 and 1967. It was said at the time that such an orbital shakedown would not be possible without a ground-launched Orion craft. Why is this? The reason is not purely technical. We could have constructed Orion in Earth orbit and then tested its systems, but this is economically impractical. The effort of orbital construction of a test vehicle would be far greater than conducting simple orbital tests of the pulse drive alone on a testbed. The tests then inform the design of vehicles built in orbit. So we have a choice. If we conduct tests of the nuclear pulse concept in orbit, we will optimize our vehicle design to incorporate our findings, requiring separate test and fielding phases, which will require proving 2 or more different engines, increasing the ultimate risk. While testing is a good idea, building multiple NPP engines and having to rate all of them for human flight will take considerably more time and resources, and ultimately increase risk. If we involve a ground-launched Orion in this first series of tests, we will use an over-engineered system to achieve orbit and then make adjustments to the system after performing a shakedown. This method avoids the time and cost of conducting orbital tests followed by orbital assembly, instead incorporating the goal of testing into the design of the first-generation flight vehicles. It also permits us to begin designing vehicles to be built in orbit without the uncertainty of never having flown an Orion-style engine, and any engines produced in this process will already be crew-rated. Part of the initial scientific and logistical mission of these vehicles is to better understand the effects of man-made radiation on space by conducting shakedown maneuvers around Earth and the Moon. Exact guidelines for shakedown operations are provided in the Orion program documentation and offer a baseline for us to work from today. A period of several days in Earth orbit will allow stress testing of ship systems and allow the crew to perform training in preparation for deep space activity, and this need is incorporated into several systems. We should recognize that the influence of man-made radiation in space is not yet well understood, and it is part of the scientific mission of these vehicles to establish a better understanding of these phenomena. NPS Freeman is not a first-generation vessel, but does inherit design choices evident in test vehicles. The decision to use a pusher plate with a larger-than-needed radius is the product of a design philosophy prevalent in designing NPP craft, to allow parts interchangeability with future vessels and refitting of larger ship modules. Modular and expandable design allows NPP craft to retain their value and also provides an environment where experienced crews can migrate their skills to other vehicles. Thank you for watching. I hope you enjoyed today's episode. Please like, subscribe, and comment to help grow our audience. Thank you.